to calculate the remaining matrix elements, in particular the matrix element, the first matrix element that we saw in the previous slide. So let me recall a distinction between the ket vector psi used in the Dirac notations and the wave function psi of x as it appears, let's say, in the Schrödinger equation. So the former really represents an abstract state of the system which is sort of unrelated to our choice of describing it. So it sort of doesn't rely on a particular choice of the coordinates, while psi of x is a specific what we call representation, which is much like coordinates of a vector. So the relation between the two is the following. So it's basically a matrix element, so psi of x is the matrix element between x and psi. And both are abstract vectors in some Hilbert space. Now, a particular example of this wave function, for example, is this plane wave, which describes the particle moving with a certain momentum. I don't want to discuss too much the choice of the coefficient at this stage. We're going to discuss it later in the course. In any case, we definitely have seen this function before, and we know it describes a particle with a given momentum. Now, the question that we're really asking now in relation with this matrix element, what is the wave function of a particle with a given coordinate? Let's say x prime. So, in order to answer this question, we need to remind ourselves or introduce, for those of you who don't know, the notion of the Dirac delta function, which basically is exactly this matrix elements we're after. So in order to introduce it, let me recall a few very simple facts from the usual linear algebra. So let's say if we have a finite dimensional vector space with some Cartesian coordinate system and basis vectors, let's say e1, e2, well, in principle, etc., e3, e4. So the Cartesian coordinate system implies that the dot product of two basis vectors, e sub I and e sub j, is equal to 0 if they're different, which means they're orthogonal to each other, or it's equal to 1 if this is the same vector, which means that the norm of the vector is equal to 1. And so the symbol which sort of summarizes this relation is the Kronecker delta symbol, delta ij, which is defined as so. So of course, if we're going to calculate the sum over all, let's say, i's of delta ij, we're going to have the sum equal to 1. Just because all of them are equal, all these terms are equal to 0, apart from the one where I is equal to g. Now, the difference between this sort of simplistic picture of the usual basis vectors in the usual linear vector space and the basis vectors in quantum mechanics is that the basis we're dealing now is sort of continuum basis. So the basis vectors are really sort of some ket vectors which are labeled by coordinates, and there are infinitely many coordinates, and there is sort of a continuum space of these coordinates. But if we sort of use the analogy between, let's say, ei and x and ej and x prime, so this product is much like a dot product of these two vectors. So using this analogy, we can demand, therefore, that if x is not equal to x prime, this matrix element and therefore this delta function, which is sort of a continuum version of this delta symbol, are equal to 0. And if x is equal to x prime, it's something else. And so this something else is determined by a condition which is very similar to this condition, but now instead of summing over a discrete set of vectors labeled by I, we have to integrate over a continuum set of vectors labeled by x. And so these are all possible coordinates in one-dimensional space going from minus infinity to plus infinity, and the corresponding delta function, the integral of the corresponding delta function is equal to 1. And so therefore, if we try to visualize this delta function, it's something which is equal to 0 everywhere. So this is our delta of x, and this is x. So we have something which is equal to 0 everywhere, apart from just one single point where this function is so large, it has such a huge high peak, that the integral collected from this single peak gives us a finite result. And, well, this sort of implies that the value of this delta function at x equals x prime is infinity. And these conditions are the canonical conditions that determine the Dirac delta function. Now, this Dirac delta function has many properties that can be discussed, so I don't have time for that now, but let me just mention one important property, which is essentially the Fourier transform of the delta function. So we know that any reasonable function, and in this case actually unreasonable function too, can be expanded in terms of these sort of plane wave like functions, and this expansion is called the Fourier transform. So if you Fourier transform the Dirac delta function, it will look like that. So it's essentially an integral from minus infinity to plus infinity of dk over 2 pi e to the power ikx. So these are well, things that we need now to calculate the remaining matrix elements. So one of them we in some sense have already calculated. So let me just put everything together and clean up this space a little bit. So one matrix element that we can immediately write down by analogy with this relation that we just derived is the matrix element between the neighboring points x sub k and x sub k plus 1, which can be written just in one-to-one correspondence with this result. We just replace x with xk plus 1 and x prime with x sub k, and we get this delta function of the difference, which we'll also call later on delta x. Now, in a very similar way, we can now calculate also the matrix element of the potential v of x. So since v, the potential, depends only on the coordinate, and this vector, this state vector, is the eigenstate of the coordinate, it means that v of x, when acting on the x sub k, just gives us the number v of x sub k, which can be factored out, and the remaining matrix element we just calculated, so the result is simply this. So a slightly less trivial matrix element appears from the kinetic energy, where we have to calculate the matrix element of the p squared over 2m, and so the x sub k is not an eigenfunction of momentum p. So in order to calculate it, though, we can use again the resolution of the identity that we discussed before, but now formulated for the momenta rather than for coordinates. So this guy is equal to 1, and we can insert this resolution of the identity in between this operator p squared over 2m and x sub k, and if we do so, we get this integral. So here I replaced the dummy variable of integration. Instead of writing it as p here, I just write it as p sub k. But it's the same resolution of the identity. And so here now, so the momentum operator, this kinetic energy, does act on its eigenstate. So therefore, this becomes simply p sub k squared over 2m, which is a number that can be factored out. And the remaining matrix elements, this guy and this guy, have to be compared with this expression for the plane wave. So these are simply plane waves. And so if we put everything together, for this term, we get the following result for the matrix element of the kinetic energy. So which involves an integral over momentum. In this case, p sub k is the momentum. So in order to write all matrix elements in a similar fashion, we can use this relation for the delta function, basically the Fourier transform for the delta function, and just replace k with p over h bar. So if we do so, we get essentially the same integral, but now integrated over a momentum, and the exponential here will involve I over h bar, p times x. So, but it's essentially the same expression for the delta function, and we can use it here to write the matrix element in terms of these integrals. So, and you see that all three matrix elements that appear in the in our previous calculation can be written in a very similar fashion. Now, the good news is that we have reached our final slide, and we are now in the position to put everything together and well, get to the main result of Feynman. What we have done in the previous slide, we have calculated the matrix elements that we need to describe the propagator, and so these are these matrix elements. So we write them sort of in a uniform fashion. So there is this one coming from this term, and there is a kinetic and potential energy coming from the Hamiltonian term. Now, why? Let's recall, why do we even bother, to think about this type of matrix element? So where it comes from is really the this sort of picture of the propagator. So remember, so we want to find the propagator from an initial point xi or x0 to a final point xf in a time t. And so what we did, we split the time interval from 0 to t into n very small time intervals delta t. And in doing so, we have represented our initial propagator as a product essentially of these small propagators, going, let's say, from this point to x1, from x1 to x2, etc., etc. And so basically, to calculate these many matrix elements, to calculate this u of delta t, we needed to calculate this guy, and so we have done so. So this is the expression, and now we can just use it. So notice the good thing about this expression. Well, it looks a little bit cumbersome, but the good thing about this expression is that it doesn't have any operators anymore. The operators are gone. There are no hats here. There are only numbers, the regular numbers we're used to. So another thing which we can notice is that this time interval delta t is very small, because we truncate our interval from 0 to t into n pieces, and n goes to infinity. So this guy is really small. And at this point, what we can recall is the following Taylor expansion for an exponential of some small number. So if we have a small number, let's say epsilon much smaller than 1, so the exponential can be written as 1 plus epsilon. We can neglect the other terms. So what Feynman does at this stage, he notices that, well, this term here is a small term, much like the epsilon here. And he uses this Taylor expansion sort of backwards. So instead of writing the exponential as a linear, well, 1 plus a linear term, he writes this 1 minus a linear term as an exponential. So, and this is the result that he has. So the reason he does that is because now the integral that we get is very convenient, because this is really the Gaussian integral that we know how to calculate. So you see, we have an integral over momentum, we have a quadratic term, and we have a linear term, and this is something we have seen before. So if we do the calculation of the integral, so what we're going to get is this. So just, the result of exponential m over 2 delta x squared over delta t squared. But now let's look again at this picture, which shows the trajectory. So you see, these are these trajectories, various trajectories that go from the initial point to the final point. And so here, this term sort of corresponds to a single segment, let's say this guy, where delta t is this small time interval, and delta x is really the change in the coordinate. Well, basically, you may think about the distance that the particle propagates in this time delta t. So delta x over delta t is can be interpreted as simply the velocity of the particle. So therefore, if we write it, so we can see that this matrix element is nothing but e to the power I over h mv squared over 2. So basically the kinetic energy minus the potential energy times delta t. So, and this is something which has a name in classical physics, so maybe some of you know it. And this name is called a Lagrangian. Let me call it L sub k. And so in these notations, we can write the result for the matrix element of u of delta t as simply e to the power I over h bar L sub k times delta t. So using this result, we can now rewrite our main object, this propagator, as follows. So we're going to have a bunch of integrals over x1, this point, this point, this point, of these exponentials of these Lagrangians corresponding, let's say, to the first segment, second segment, third segment, etc. So notice that essentially these integrals over x1, x2, etc. sort of correspond to moving around these points, these intermediate points between xi and xf. The endpoints are completely fixed, but the intermediate points are free. And these integrals essentially symbolize this freedom. So now the last step here in the derivation is just to recognize that, so here the product of the exponentials, it can be written as an exponential of the sum, I over h bar L sub k delta t. And as delta t, the time interval goes to 0, we can simply write it as e to the power I over h bar, an integral, well, from 0 to t, L dt. And the integral of the Lagrangian over time is is known as classical action. So what we got is essentially the main result, that the propagator can be written as an integral over all possible trajectories, all possible intermediate coordinates, of the weighted with this exponential of the classical action. So this is the result that we sort of advertised in the very beginning. And Feynman introduced essentially a symbol, a notation, instead of writing a bunch of these intermediate steps. So he can introduce a single symbol, which is this capital curly D of x of t, which is called the path integral. So it's just a symbol. But it turns out that it's actually a very convenient symbol. So now our derivation is over. So this is the main result. So maybe let me just write it, underline it again. So this is our main result. And so I know it's been a very long derivation, but as we'll see in the next lecture, so this result is extremely useful in that it will allow us to get, well, from now on, without extraordinary calculations, extremely profound and interesting physical facts. So we're going to discuss the correspondence between classical and quantum mechanics. We're going to discuss so-called quantum localization. We're going to discuss a very interesting process of quantum dissipation. So there are a lot of cool things that can be studied now with this object. But, well, it did take us a while to derive it. So I hope some of you got the main points of this derivation.